Balancing chemical equations. Balancing of a chemical equation may be defined as the method of making the number of atoms of different elements on both the sides of the equation equal. The balancing of chemical equation can be done with the help of hit and trial method. In this method, the coefficients before the symbols or formulae of the reactants and products are adjusted in such a way that the total number of atoms of each element on both the sides of the arrowhead becomes equal. This balancing is also known as mass balancing because if the atoms of elements on both sides are equal, then their masses will also be equal. Let us discuss the major steps involved in balancing a chemical equation. 1. Write the chemical equation in the form of a word equation. Keep the reactants on left side and the products on right side. Separate them by an arrow pointing from reactants towards the products. 2. Convert the word equation into a symbol equation by writing the symbols and formulae of all the reactants and products. 3. Make the atoms of different elements on both sides of the equation equal by a suitable method. This is known as balancing of equation. Do not change the formulae of the substances while balancing the equation. Let us illustrate the balancing of chemical equations with the help of an example. 1. Zinc reacts with dilute sulfuric acid to give zinc sulfate and hydrogen. Solution. The word equation for the reaction is zinc plus sulfuric acid gives zinc sulfate plus hydrogen. The symbol equation for the same reaction is zinc reacts with sulfuric acid to give zinc sulfate and hydrogen. Count the number of atoms of all the elements on the reactant side and then the number of atoms of all the elements on the product side, that is, on both the sides of the equation. As the number of atoms of all the elements involved in the reactants and products are equal, the equation is already balanced. Let us have a look at another example. The word equation for the reaction is magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen. Let us try to find the solution. The symbol equation for the same reaction is Mg reacts with HCl to give MgCl2 plus H2. The balancing of the equation is done through the following few steps. Step 1. Count the number of atoms of all the elements in the reactants and then of products, that is, on both the sides of the equation. You can see that the number of magnesium atoms are equal to 1 on both the sides. At the same time, the number of chlorine and hydrogen atoms is not equal. Step 2. It is always convenient to start with the compound that contains the maximum number of atoms, whether of reactants or of products. Then use appropriate coefficients to balance its atoms. In this case, the compound is magnesium chloride. Here, the magnesium atoms are already balanced on both sides. To balance the atoms of chlorine, put coefficient 2 before HCl on the reactant side. The equation may be written as Mg reacts with 2HCl to give MgCl2 plus hydrogen. Step 3. Now check the number of atoms of different elements on both the sides of the equation. These are equal. This means that the equation is balanced. Let us take another example. Iron reacts with water to form ferric oxide, liberating hydrogen gas. And now the solution. The word equation for the reaction is iron reacts with water to give ferric oxide plus hydrogen. The symbol equation for the same reaction is iron Fe plus H2O gives Fe2O3 plus H2. The balancing of the equation is done in the following steps. Step 1. We count the number of atoms of all the elements in the reactants and products on both the sides of the equation. A look at equation reveals that the number of hydrogen atoms are equal on both the sides. At the same time, the number of iron and oxygen atoms are not equal. Step 2. On inspection, the number of oxygen atoms in the reactant, that is water, is 1, while in the product ferric oxide, these are 3. To balance these atoms, put coefficient 3 before H2O on the reactant side. The partially balanced equation may be written as Fe plus 3H2O gives Fe2O3 plus H2. Step 3. In order to equate hydrogen atoms, put coefficient 3 before H2 on the product side. As a result, the hydrogen atoms on both sides of the equation become 6 and thus are balanced. The partially balanced equation may now be written as Fe plus 3H2O gives Fe2O3 plus 3H2. Step 4. In order to balance the iron atoms, put coefficient 2 before Fe on the reactant side. The equation formed may be written as 2Fe plus 3H2O gives Fe2O3 plus 3H2. Step 5. On final inspection, the number of atoms of all the elements on both sides of the equation are equal. Therefore, the equation is balanced. We will now discuss another example. Methane burns in oxygen to form carbon dioxide and water. Here is the solution. The word equation for the reaction is methane plus oxygen gives carbon dioxide plus water. The symbol equation for the same reaction is CH4 plus O2 gives CO2 plus H2O. Following are the steps to balance the equation. Step 1. Let us count the number of atoms of all the elements in the reactants and the products on both sides of the equation. Number of carbon atoms are equal, that is 1 on both sides. At the same time, the number of hydrogen and oxygen atoms is not equal. Step 2. The number of hydrogen atoms in the reactant CH4 is 4, while in the product water these are 2. To balance the hydrogen atoms, put coefficient 2 before H2O on the product side. The partially balanced equation may be written as CH4 reacts with O2 to give CO2 plus 2H2O. Step 3. Further, number of oxygen atoms in the product is 4, while these are 2 in the reactant side. In order to equate oxygen atoms, put coefficient 2 before oxygen on the reactant side. The equation may be written as CH4 reacts with 2O2 to give CO2 plus 2H2O. Step 4. On final inspection, number of atoms of all the elements on both the sides of the equation are equal. Therefore, the equation is balanced. Writing symbols of physical states. The physical states are also mentioned with the help of specific symbols known as state symbols. S for solid state, L for liquid state, G for gaseous state, AQ for aqueous state. Na in solid state reacts with 2H2O in liquid state to give 2NaOH in aqueous state plus hydrogen in gaseous state or H2 with an up arrow. This equation shows sodium is in solid state, water is in liquid state, sodium hydroxide is in aqueous state, and hydrogen is in gaseous state. Up arrow reveals that gas is liberated. CaOH whole twice in liquid state reacts with carbon dioxide in gaseous state to give CaCO3 with a down arrow and H2O in liquid state. The state symbols are of utmost significance for those chemical reactions which are accompanied by evolution or absorption of heat. They can be exothermic or endothermic. 2H2 in gaseous state reacts with oxygen in gaseous state to give 2H2O in liquid state along with 572 kilojoules of energy. This is an exothermic reaction in which heat is evolved. N2 in gaseous state reacts with oxygen in gaseous state to give 2NO in gaseous state, absorbing 180 kilojoules of energy. This is an endothermic reaction in which heat is absorbed. In some chemical reactions, conditions of temperature, pressure, catalyst, etc. are mentioned either above or below the arrowhead that separate the reactants from the products. Gaseous nitrogen reacts with gaseous hydrogen in the presence of iron catalyst at 500 degrees centigrade and 200 atmospheric pressure to form ammonia in gaseous state. Carbon dioxide in gaseous state reacts with water in the liquid state in the presence of sunlight and chlorophyll to form carbohydrate in aqueous state and oxygen in gaseous state. Certain chemical reactions proceed in both directions. The reactants change into products in forward reaction. The products are converted into reactants in the backward reaction. In the forward reaction, nitrogen reacts with hydrogen to form ammonia. In the backward reaction, ammonia splits up to form nitrogen and hydrogen. Such reactions are called reversible reactions. Let us revise. Information conveyed by a chemical reaction. A chemical reaction tells about reactants and products participating in the reaction. A chemical reaction informs us about the symbols and formulae of all substances involved in the reaction. It tells us about the atoms and molecules of the reactants and products that are involved in the reaction. It gives us information about the weights of the reactants consumed and of the products formed in the reaction. It tells us about number of gram atoms or gram moles of the substance that are participating in the reaction. In few cases, it tells us about the physical states of the reactants and the products, and also about the heat evolved or absorbed during the reaction. A chemical equation does not tell us about the feasibility of a chemical reaction. Example: copper reacts with sulfuric acid to give copper sulfate and hydrogen. This reaction seems to be feasible but does not take place. We cannot get any clue about the rate of reaction from a chemical equation. This means that it does not tell us whether the reaction is slow or fast. Balancing ionic equations. Ionic equations are those chemical equations which represent chemical reactions involving ionic substances in their aqueous solutions. Let us take an example to understand it better. What really happens when you put AgNO3 and NaCl both in water? AgNO3 in aqueous state reacts with NaCl in aqueous state to give AgCl in solid state plus NaNO3 in aqueous state. Key point is sodium chloride actually means the sodium ions and the chloride ions are present in aqueous state. These exist as dissociated ions or ions in solution. Magnesium nitrate in aqueous solution really means that the magnesium ions and the nitrate ions are in dissociated form or ionic form. MgNO3 whole twice in aqueous state really means magnesium positive 2 ions in aqueous state plus NO3 negative 1 ions in aqueous state. That is dissociated ions or ions in solution. Let us first try to understand what is dissolving. When an ionic compound, for example a salt, dissolves in water, the compound dissociates. That is, It breaks apart into cations and anions. Example: CaNO3 whole twice in solid state gives Ca 2 positive ions in aqueous state plus 2 NO3 negative ions in aqueous state. When a covalent compound, for example sugar, dissolves in water, the molecules simply disperse. They do not dissociate. Molecules of the covalent compounds simply disperse due to attraction with polar water molecules. Key point: AgCl in solid state really means solid silver chloride. Let us take an example to understand it better. What really happens when you put silver nitrate and sodium chloride both in water? Silver nitrate in aqueous state reacts with sodium chloride in aqueous state to give silver chloride in solid state plus sodium nitrate in aqueous state. Here, silver nitrate dissociates into silver ions and nitrate ions. Sodium chloride dissociates into sodium ions and chloride ions. Silver ions combine with chloride ions to form silver chloride precipitate. Sodium ions and nitrate ions remain in solution. Silver chloride in solid state settles as a precipitate at the bottom of the container. Only sodium ions and nitrate ions remain in solution in ionic form. We can say that sodium nitrate is present in aqueous form. So, we can say that AgNO3 in aqueous state reacts with NaCl in aqueous state to give AgCl in solid state plus NaNO3 in aqueous state. The complete ionic equation can be written as Ag positive ions in aqueous state plus NO3 negative ions in aqueous state plus sodium ions in aqueous state plus chlorine ions in aqueous state give AgCl in solid state plus nitrate ions and sodium ions. This means that reaction has taken place between silver and chloride ions to form silver chloride. No reaction takes place between sodium ions and nitrate ions. This means these ions do not participate in the reaction. They are called spectator ions. The net ionic equation is constructed from the complete ionic equation. Crossing over the spectator ions, we get silver ions in aqueous state plus chloride ions in aqueous state gives solid silver chloride. Let us revise. Complete molecular equation describes double replacement reaction. Complete ionic equation more accurately shows the reacting species as ions and the products either as ions or a precipitate. Net ionic equation focuses only on the ions reacting. Spectator ions are those ions that are present in solution but do not participate in the reaction. We can say that a chemical equation written in terms of ionic symbols is called an ionic equation. For example, the equation shown on screen is an ionic equation. Zn in solid state reacts with two H positive ions in aqueous state to give Zn two positive ions in aqueous state plus H2 in gaseous state. Similarly, copper ions in aqueous state react with zinc ions in solid state to form zinc ions in aqueous state, and copper is formed in solid state. This is also an ionic equation. It is not necessary that all the reactants and products of a chemical reaction be expressed as ions for it to qualify as an ionic equation. So, Cd, two positive ions in aqueous state, react with H2S in gaseous state to give CdS plus two H positive ions in aqueous state. Equation on screen is also an ionic equation. Hydrogen sulfide and CdS are written in unionized form. A few examples of ionic equations are shown on screen. Hydrogen chloride in an aqueous form reacts with sodium hydroxide in an aqueous form to form sodium chloride in an aqueous form and water in liquid form. Hydrogen ions, chloride ions, and hydroxide ions in aqueous state react to form sodium ions, chloride ions in aqueous state, and water in liquid state. Cancelling out any positive and Cl negative ions on both sides of the equation, the new ionic equation becomes H positive ions in aqueous state plus OH in aqueous state give H2O in liquid state. From this equation, we find that a neutralization reaction between an acid and a base has taken place. Let us discuss another neutralization reaction. The reaction between potassium hydroxide and hydrochloric acid in an aqueous solution can be written as KOH in aqueous state reacts with HCl in aqueous state to give KCl in aqueous state plus H2O in liquid state. K positive ions in aqueous state plus OH negative ions in aqueous state plus Cl negative ions in aqueous state give K positive ions in aqueous state plus Cl negative ions in aqueous state plus H2O in liquid state. On cancelling out the common factors of K positive in aqueous state and Cl negative in aqueous state on both sides of the equation, the new ionic equation becomes H positive ions in aqueous state plus OH in aqueous state gives H2O in liquid state. We can conclude that neutralization is mainly the formation of water from H positive ions in aqueous state and OH negative ions in aqueous state. The reaction of zinc metal with dilute sulfuric acid can be represented in the form of an ionic equation, which can be represented as shown on screen. Zn in solid state reacts with 2H positive in aqueous state to give Zn 2 positive ions in aqueous state and H2 gas. Instead of Zn in solid state reacts with dilute H2SO4 to give ZnSO4 in aqueous state and H2 in gaseous state. We will take another example. When H2S gas is passed through a solution of cuprous ions, Cu 2 positive ions, a black precipitate of copper sulfide and hydrogen ions are formed. The representation of a reaction of this kind has an added advantage that the above ionic equation is applicable for solution of cuprous ions obtained from any ionic source of copper like copper sulfate, that is CuSO4, copper nitrate, CuNO3 whole twice, copper chloride, CuCl2, and so on. When zinc metal is added to solution of cuprous ions, Cu 2 positive ion, it dissolves to form Zn 2 positive ion and the copper metal gets precipitated. The source of cuprous ions, that is Cu 2 positive ions, can be any water-soluble salt of copper, like copper sulfate, that is CuSO4, copper nitrate, CuNO3 whole twice, copper chloride, CuCl2, and so on. We will now discuss about balancing ionic equations. Ionic equations, like ordinary chemical equations, should be balanced in terms of the number of atoms of all kinds. Additionally, an ionic equation must also be balanced with respect to the number of charges on both sides. The skeletal ionic equation involving aluminium metal and an acid that liberates hydrogen gas can be written as Al in solid state reacts with H positive ions in aqueous state to give Al 3 positive ions in aqueous state plus H2 gas. Such equations must be balanced first for the number of atoms or ions only. That is, element aluminium, the number of atoms on left hand side is 1 and the number of atoms on right hand side is also 1. Element hydrogen, the number of atoms on left hand side is 1 and the number of atoms on the right hand side is 2. Balance the number of hydrogen atoms by putting 2 before hydrogen ions in aqueous state. The new equation becomes Al in solid state reacts with 2 H positive ions in aqueous state to give Al 3 positive ions in aqueous state and H2 gas. This equation is balanced with respect to aluminium and hydrogen atoms, but this is an unbalanced equation with respect to charges. In order to balance it completely, put 6 before H2 positive ions in aqueous state instead of 2 and 2 before Al3 positive ions in aqueous state to make 6 positive charges on both sides. Al in solid state reacts with 6 H positive ions in aqueous state to give 2 Al 3 positive ions in aqueous state and H2 in gaseous state. Again, balance the aluminium atoms by putting 2 before Al in solid state and 3 before H2. 2Al in solid state reacts with 6 H positive ions in aqueous state to give 2Al 3 positive ions in aqueous state and 3H2 in gaseous state. This equation is completely balanced both with respect to its number of atoms and the number of charges, and thus can be called a completely balanced ionic equation. Children, let us Balance the following ionic equation. Cu, two positive ions in aqueous state, react with Fe in solid state to give Fe, three positive ions in aqueous state, and Cu in solid state. Solution is: on inspection, it is clear that the number of atoms on both sides of the equation is same. One atom or ion of Fe and one atom or ion of Cu. So, it only needs to be balanced with respect to charges. To make charges equal on both sides, put 3 before Cu, two positive ions in aqueous state, and 2 before Fe, three positive ions. But during the process, the number of atoms becomes unequal. To make them equal, put 2 before Fe in solid state and 3 before Cu in solid state. The equation thus becomes 3Cu, two positive ions in aqueous state, react with 2Fe in solid state to give 2Fe, three positive ions in aqueous state, and 3Cu in solid state. This equation is completely balanced.